Okay, so I just made a video going through the basics of implicit differentiation, and I just wanted to make another short video with a couple more examples so you can see these things worked out, because they can look a little confusing when you look at them. So suppose I have xy cubed plus x squared y equals x. Find y prime. And again, as I mentioned before, I'm deliberately going back and forth from Leibniz to prime notation so you get used to seeing both of them. So we said that's a product, so I apply the product rule. It's the first x times the derivative of the second. The derivative of y cubed is a chain rule. Bring down the 3, inside stays the same, lower the power by 1 to a 2, times the derivative of the inside, which is y prime. And now, like I said in the last video, this is where sometimes students will get confused. They'll stop here and jump to the next one. Product rule. First, derivative of second, plus the second, which is y cubed, times the derivative of the first, the derivative of x is 1. That's all the derivative of this thing. Now I do this, which is another product rule. So it's the first, x squared, times the derivative of y. The derivative of y is just y prime, plus the second, which is y, times the derivative of the first. The derivative of x squared is 2x. That's my second product rule right here. Oh, sorry, so I have product rule equals the derivative of x, which is 1. Now I want to solve for y prime. Keep in mind, I think one of the reasons people might use the Leibniz for this a lot more is because now you have y primes, but with all the powers floating around, that can sometimes be confusing. So dy dx, the Leibniz version, might make it easier to see. But we isolate the y primes. So over here I get, let's see, if I rearrange this one, that's 3xy squared y prime, plus rearrange this one, or I don't really have to, that's x squared y prime, equals, everything else goes to the right, so that's 1 minus y cubed minus 2xy when I rearrange that. Now I factor out the y prime, and I get 3xy squared plus x squared equals 1 minus y cubed minus 2xy. And then I divide the coefficient. Y prime equals 1 minus y cubed minus 2xy all over 3xy squared plus x squared. And again, as we've said before, there's understanding the trick. Treat the y's as implicit functions and differentiate accordingly. The rest of this is just apply derivative rules and do a whole lot of algebra. There is one more step you can sometimes take with this. You could maybe ask, what is dy dx at the point 1, 1? Then you just plug in x equal to 1, y equal to 1, and you're done. You could say, where does this have a horizontal tangent? Horizontal tangent means the slope is 0. So I just figure out where this is 0, and I would solve this. I'm not going to do it for this one because this won't work out nicely. But if you had a problem like that, the algebra would work out. You could ask, where is the slope undefined? It's undefined when the denominator is 0. Again, this one won't work out nicely, but in that case, you would just set the denominator equal to 0 and solve. So there's a lot more you can do with this, but it's essentially all algebra you've actually done since pre-calc. Solve a problem and then plug stuff in. Either plug in an x and a y that you're given to get the slope at a point, or they give you the slope, the y prime, and you find the x's and the y's that make it work. So be aware, there's more you can do with this. There's a lot of applications we're going to do with it too. But the algebraic principles are the same as they were in pre-calc before. Solve the problem, and then given x find y, or given y find x, essentially. Suppose we have this. X sine y plus cosine x equals y. I want to find the derivative. This should be fun. So first, now we're going to write it in terms of Leibniz, so we'll go with dy dx. This is a product, so it's the first x times the derivative of the second. Keep in mind this is still a chain rule. Outside function sine, inside function y. So the derivative of this is the chain rule. the outside, take the derivative of the outside, the derivative of sine is cosine, inside function stays the same, times the derivative of the inside, which is dy dx. I am not done. This is just the first half of the product rule. First, derivative of a second, plus the second, which is sine y, times the derivative of the first. The derivative of x is just 1, so that just drops out. There's my product rule, plus, now the derivative of this. This is just a regular trig function. The derivative of cosine is negative sine x. Equals the derivative of y, that's dy dx. Now to solve for dy dx, in this case, since I have this by itself on the right, I'm going to subtract this term over. So I'll be left with, on the left, sine y minus sine x equals dy dx minus x cosine y, dy dx. And now again, it's just algebra. Factor out the dy dx, and you get sine y minus sine x equals dy dx times 1 minus x cosine y. And then I divide that over. So I get dy dx equals sine y minus sine x over 1 minus x, I dropped my x, 1 minus x cosine y. And I'm done. And one thing I would point out that at this point I'm assuming is pretty obvious. I mean, you've all done pre-calc and trig before. Essentially, we learn a trick, say product rule or quotient rule, and you apply it to what you know. At the time, we basically knew polynomials. And then you learn more advanced derivatives, say derivatives of trig functions. And then you start getting problems that have both polynomials and trig functions where you have to apply the product rule and the quotient rule. As of right now, for implicit differentiation, we really only know the derivatives of polynomial things, essentially, as well as trigonometric things. And we can combine the two and do implicit differentiation. There are still more functions that we will learn the derivatives of, and then once we learn them, we could just as easily throw them into this implicit differentiation. So be aware, right now we're restricting ourselves to the functions we know, but as we learn more functions and their derivatives, we can just as easily come back to this and plug those in here and get more complex implicit differentiation problems, but the principle will always be the same. Write it out, figure out where you have products, where you have chain rules, what is a variable, what is a function, and then apply all the appropriate derivative rules multiple times.